small earthquakes rattled an area outside Mount. The largest of the 13 quakes was a magnitude 3.9.
The earth beneath Mount St. Helens had been whispering, rattling with tremors too subtle for many to sense, too complex for casual listeners to interpret. But then, high, so high it was invisible without the watchful eyes of space-based sensors, a satellite detected something unprecedented, molten rock shifting, pulsing deep in the vessel of the volcano. That discovery prompted the US Geological Survey to issue the rare and most serious level of a warning, a red alert, and with that, the slumbering giant was thrust into a new state of tension. Before we start, smash the like and subscribe buttons for more updates. The red alert, more than just a bureaucratic term, is a vivid declaration of heightened danger. It signals that hazardous volcanic activity is either underway or imminent. Such a designation instantly transforms what might have seemed a remote scientific curiosity into an emergency with real-world stakes. When satellites flagged that magma was on the move, they didn't just observe heat or seismic fuzziness. They revealed molten rock forging new pathways, reshaping the subterranean plumbing of the volcano. That movement tells a story of pressure building deep underground, of magma making its way toward the surface, potentially readying for an explosive release. That subterranean ballet, silent yet powerful, is what triggered this urgent alarm. To understand why this matters so urgently, it's helpful to remember the volcano's long history. Nearly half a century ago, Mount St. Helens awoke in April 1980 with swarms of earthquakes and bulging deformation that heralded the catastrophic eruption of May. The summit's north flank grew outward, a sign that magma was gathering like a pent-up gas preparing to be expelled. So satellite-detected magma movement today stirs echoes of that past, a reminder that beneath the surface, time and distance fall away in the face of nature's raw energy. The red alert is more than warning. It's a signal that history may be repeating or rewriting itself. That alert has immediate ramifications. Agencies responsible for safety must spring into action. Air traffic controllers adjust plans and issue warnings. Ash spewed during eruptions can devastate jet engines and scatter debris across flight paths. Local authorities must assess critical infrastructure. Roads, bridges, water systems, electric lines, and communication networks all hang in the balance if an eruption were to unfold. Nearby communities suddenly find themselves suspended between calm and chaos. The air becomes thick with tension. Schools, businesses, and transportation routes enter a state of preparedness or suspension. All around, people look skyward, wondering if the mountain will roar and offer a terrible reminder of its power. Scientists on the ground and in remote monitoring posts shift into high gear. Seismologists, gas specialists, climatologists, geodesists all turn their instruments from steady monitoring to high-alert vigilance. Seismographs search for tremors and shifts. Gas sensors track sulfur dioxide and carbon dioxide release. Thermal cameras watch for hot spotting, and satellites record every flicker of ground deformation. Each dataset becomes a pixel in a quickly forming image of risk. Communications channels light up with messages intended for the public. Alert levels, aviation advisories, hazard zones. Every term must be precise and calibrated, conveying urgency without panic. Warnings cascade through social media, emergency broadcasts, local government channels, and press briefings, dressing the landscape with anticipation. Meanwhile, the underworld of magma is rewriting itself. Pathways may crack open, pressure chambers may distend, and magma may escalate its ascent. It is a fluid, dynamic process. What satellites capture is only the beginning, a hint of channels forming, of molten rock inching upward. But that is enough to change everything above. The scientific community also recalibrates its modeling in real time. The new data modifies existing simulations, sharpening forecasts of where and how fast magma could reach the surface. Geographic and demographic overlays merge with simulations of potential lava flows, pyroclastic surges, and ash dispersal. That data matrix becomes the backbone of response planning. Evacuation thresholds, road closures, contingency for critical facilities, and protection of cultural or ecological treasures. Meanwhile, the broader volcanic monitoring world turns its gaze to this event. Symposiums, research centers, emergency agencies around the globe register the alert. Lessons learned here, captured in real time, will inform how other regions assess risk when satellites reveal magma motion. The scientific community treats this intrusion into the subterranean world with fascination and gravity. In the heart of the mountain, pressure mounts. The magma itself doesn't care for human calendars or crisis plans. It flows driven by pressure, buoyancy, fractures, and temperature. That molten material doesn't speak, and yet when it moves, it tells everything about the forces in play beneath. The red alert, though alarming, is a vital part of modern resilience. Without it, communities would sleep on a warning too late. With it, even as anxiety rises, people can act. Roads closed, flights redirected, residents prepped to evacuate if needed. That preparedness may look like caution today, but it may save lives tomorrow. As the alert status lingers, every hour becomes laden with significance. Scientists monitor every tremor, shift, and emission. Models update, scenarios sharpen, maps are redrawn, communities hold their breath. For some, life carries on with anxious calm. For others, the red alert is the hinge between normalcy and the extraordinary. This moment, defined by satellite intelligence and geological urgency, marks the intersection of modern monitoring technology and ancient Earth processes. It shows how our gaze from space can detect deep and hidden shifts, giving us a window into processes otherwise invisible. And when those shifts occur beneath a volcano with a potent history like Mount St. Helens, they become more than geology. They become a summons to watch, to prepare, to respect the power beneath our feet. In the hours that follow, every data point may shift the narrative. Smaller movements may ease pressure, or magma may continue its ascent. The red alert functions as both shield and alarm bell, giving space for action before eruption forces nature's hand. And so, beneath the watchful stars, and observed by instruments calibrated to sense heat, motion, and gas, the mountain pulses. Humanity watches in tension and hope, armed with the knowledge that while we cannot stop magma, we can listen, and respond with foresight and care. That capacity to listen, enabled by satellites and science, may be the margin that matters when molten rock presses upward, carrying with it the memory of past eruptions and the warning of what may come. The red alert at Mount St. Helens had become more than a technical classification. It was an atmospheric shift that reached into the psychology of the region. From small towns scattered along the shadow of the volcano to the farthest corners of the scientific community, it pulled focus toward the mountain in a way that could not be ignored. The mountain's presence, already monumental, began to dominate every horizon, both literal and mental. At the core of the situation was the satellite detection itself, the quiet yet decisive act of spaceborne instruments reading the signature of magma on the move. These were not vague thermal blips or ambiguous anomalies. The sensors measured patterns of heat, ground inflation, and changes in gravitational fields that together revealed a clear message. Something was shifting deep below. This data wasn't conjecture. It was a structured series of readings spanning days, each showing an intensifying trend. By the time the pattern had solidified, the alert had moved swiftly up the chain of decision-making. The transition from orange to red was not ceremonial. It was grounded in thresholds carefully defined by decades of observation and calibrated to minimize both false alarms and fatal delays. Those thresholds are not arbitrary. They balance a profound tension between underreaction and overreaction. If a warning comes too soon or without sufficient evidence, it can erode public trust and trigger costly, unnecessary disruptions. Too late, and it risks lives, property, and ecosystems. In the case of Mount St. Helens, the decision to escalate to red reflected an unambiguous confluence of data points: rapid magma movement, swelling ground deformation, and the complex choreography of micro-earthquakes indicating fractures opening in the volcanic edifice. As the news spread, local and regional emergency management networks began operating in synchronized fashion. Operations centers, staffed with specialists who had trained for exactly this kind of escalation, shifted into coordinated planning mode. Communication lines were tested and retested, ensuring redundancy if primary channels failed. Geographic Information Systems (GIS) teams layered hazard zones over population density maps, refining their assessments of which communities might face the first and greatest risks if the situation advanced. Meanwhile, in laboratories far from the mountain, teams of volcanologists began pulling historical data sets from prior activity cycles, looking for analogs. The 1980 eruption loomed large in these comparisons, but more recent dome-building events and smaller eruptions in the early 2000s also offered insight. These researchers weren't trying to predict the aftermath. They were using the patterns of magma behavior to assess what was unfolding right now, in the hours and days immediately surrounding the alert. The natural world itself was responding in ways subtle and dramatic. Animals inhabiting the mountain's flanks, elk, mountain goats, black bears, reacted to shifts that human senses could not perceive. Changes in the scent of the air, slight tremors, or the inaudible low-frequency rumble of the mountain's shifting heart may have already altered their movement patterns. In rivers and streams that wind away from the volcano, sediment levels were being watched closely. Any sudden discoloration or change in temperature could hint at altered underground water channels, another sign of the mountain's internal reconfiguration. Above the summit, the sky became a constant frame of reference for those living nearby. Even in the absence of ash plumes or visible steam vents, the air seemed charged, as though the sheer potential of the mountain's activity could be felt. For residents with clear views of the crater, every cloud bank was scrutinized, every wisp of mist interrogated for its origin, weather or volcanic venting. The red alert also reverberated into industries not immediately thought of as tied to volcanic activity. Airlines, especially those routing flights along the busy Pacific Northwest corridors, integrated updated monitoring data into their flight planning. Ash particles, even in small amounts, can scour turbine blades, clog sensors, and obscure visibility. For agricultural producers in the surrounding valleys, the thought of ashfall, no matter how hypothetical, prompted early steps to safeguard crops and livestock. Greenhouses were checked for ventilation seals. Irrigation systems were prepped in case rapid cleaning of plant surfaces became necessary. Seismic monitoring stations, part of a larger network scattered across the Cascades, began feeding data at higher sampling rates. Even the smallest earthquakes could carry clues, their depth, frequency, and distribution creating a kind of seismological fingerprint of the magma's progress. Scientists parse this information with algorithms designed to detect not just movement, but acceleration, because in volcano monitoring, rate of change is often more telling than absolute magnitude. Public reaction was layered. There was curiosity, fear, and in some cases a kind of awe. For some, living in proximity to the volcano had always been a conscious choice, an acceptance of both the beauty and the risk of the Cascades. Others were caught off guard, realizing only now the depth of their vulnerability. The red alert stripped away any sense that the volcano was a distant, dormant backdrop. It was a reminder that the mountain was alive in the most literal geological sense. Within scientific circles, the discussion turned to the role of space-based observation in changing how we experience these moments. In earlier decades, the first sign of magma movement might have come only after days or weeks of ground-based monitoring. Now, satellites orbiting hundreds of miles above could pick up the earliest signs of activity, measuring ground uplift in millimeters and detecting heat through thick cloud cover. This capability not only improves response times, but also changes the psychology of hazard awareness. Events that once might have gone unnoticed until they were well advanced are now detected at inception. The role of communication in this stage cannot be overstated. Information had to be both immediate and accurate. Local leaders, scientists, and media outlets walked a narrow path between urgency and alarmism. Every phrasing choice mattered. Magma movement detected was factual and precise, but magma rising toward the surface carried a different weight in the public imagination. Both might be technically accurate, yet one could trigger panic, the other preparation. Those in charge of messaging understood that the words they chose would influence not only perception, but behavior. The cultural resonance of Mount St. Helens deepened the weight of the alert. For many, the volcano is a living archive of stories, scientific, personal, and ancestral. Indigenous communities have long held traditional knowledge of the mountain's rhythms and character, narratives passed down through generations. In the context of a red alert, these cultural memories resurfaced, providing a framework of respect and caution toward the forces at play. On the technical front, engineers monitored the structural health of monitoring stations themselves. Volcanic unrest can damage the very instruments needed to track it. Remote power supplies, solar panels, and antenna arrays were inspected in anticipation of conditions that could degrade their performance. Data integrity was paramount. In a fast-evolving scenario, even brief outages in measurement could obscure critical developments. Meteorological teams became vital partners in the response effort. While no eruption had yet occurred, wind patterns, precipitation forecasts, and temperature profiles were all integrated into contingency models. These inputs would shape evacuation routes, influence the positioning of response teams, and determine which regions might be most impacted by airborne material should the volcano vent. For those in academia, the alert created a living laboratory. Graduate students, postdoctoral researchers, and seasoned professors alike saw in this event a rare convergence of technology, earth science, and public policy. Research proposals were being rewritten in real time to incorporate the unfolding conditions, with the understanding that the data captured now could fuel studies for decades. Energy companies also entered a state of heightened attention. While Mount St. Helens does not sit atop a dense matrix of pipelines or power plants, the interconnected nature of regional grids meant that any disruption, physical or economic, could ripple outward. Hydroelectric facilities downstream would be monitoring for any sign of sediment influx that might clog turbines or alter water flow. In the quieter moments between official updates, people found themselves listening differently to their surroundings. The faint rumble of a truck on a distant road could trigger a momentary flicker of anxiety. The scent of wood smoke in the evening air, carried from a neighbor's chimney, might prompt a glance toward the mountain to ensure no plume had begun to rise. The red alert had created a heightened sensory awareness, turning ordinary stimuli into potential signals. In scientific hubs, there was also an awareness of the limits of prediction. Volcanoes can be capricious, with magma movements that stall or reverse, pressure that dissipates rather than escalates. This unpredictability does not lessen the urgency of the alert. Rather, it underscores why such warnings exist at all. The red alert is not a prophecy, it is an acknowledgement that the current state carries significant risk. Even as these human and institutional systems adjusted, the geological processes continued indifferent to them. Magma surged into new chambers, some possibly ancient and partially solidified, reheating rock and forcing gases out of solution. These gases, primarily water vapor along with carbon dioxide and sulfur dioxide, rose through cracks and fissures, potentially altering the chemistry of groundwater or escaping silently into the air. In the world of disaster preparedness, scenarios were being gamed out down to minute details. Where would emergency shelters be established? How would medical supplies be allocated? Which roads could serve as both evacuation routes and access points for responders? These plans were not reactive. They were preemptive moves in a chess game where the opponent is both immensely powerful and completely inhuman. The aviation sector's adjustments went beyond rerouting. Maintenance crews prepared for the possibility of increased air filtration demands, and pilots were briefed on procedures for avoiding or safely exiting ash-contaminated airspace. Coordination between the USGS, the Federal Aviation Administration, and meteorological services ensured that any change in volcanic status could be communicated in minutes, not hours. Elsewhere, ecologists considered the short-term and long-term implications for wildlife corridors, migration patterns, and habitat integrity. While the immediate focus was on human safety, the web of life surrounding Mount St. Helens was equally poised to be reshaped by whatever the volcano might choose to do. The alert also acted as a catalyst for broader conversations about hazard readiness in the Cascades. Mount St. Helens was the focus, but other volcanoes in the chain, Mount Rainier, Mount Hood, Mount Adams, share similar geologic underpinnings. The red alert became a kind of living reminder that the region's beauty is inseparable from its volatility. In the realm of infrastructure, planners revisited vulnerabilities that might otherwise have remained abstract. Could bridges withstand seismic shaking? Were reservoirs equipped to handle sudden influxes of meltwater? Were communication towers distributed in such a way that signals could bypass damage zones? The presence of the red alert stripped away the luxury of deferral. These questions demanded attention now. In homes, preparedness kits were checked and restocked. Even without evacuation orders, residents understood the wisdom of readiness: extra water, non-perishable food, masks to filter ash, batteries for radios. For families with members requiring special care, from infants to the elderly, plans were quietly rehearsed. Who would carry what? Which vehicle would be used? Where to meet if separated? The mountain, for its part, gave no acknowledgement of the human stirrings around it. Its processes, honed over millions of years, unfolded at their own pace. Magma is patient, but when it moves, it does so with a determination that defies resistance. The red alert was humanity's recognition of that truth, a signal not of control but of awareness. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on this red alert? What do you expect will happen? We want to hear from you. Thank you for watching, and see you next time.